Welcome to recording 1A for section 7.3 of the text on absolute value equations, Unit 7, Chapter 7 of Mathematics 2200. We're going to look at how we can solve absolute value equations graphically. In this case, we have the absolute value of negative 3x minus 6 equals 3. So to solve this, we graph each side of the equation. So the right side is 3, so that we set that equal to y. Y equals 3. That graph is pretty straightforward. It's just a horizontal line. For the other one, y equals absolute value of negative 3x minus 6, I'll use the reflection method we learned back in section 7.2. So I start with the expression inside the absolute value signs. So that's y equals negative 3x minus 6. The x-intercept I find by putting 0 in for the y. So 0 equals negative 3x minus 6. And that gives me 6 equals negative 3x. Divide by negative 3, I have negative 2 equals x. Now the y-intercept. I substitute 0 for the x, and I get y equals negative 6. So I graph that. Draw that graph dashed because it's only a guide. I think I'll turn that one black because it is my guide. For my absolute value graph, any portion of the guide graph that is already positive, I keep positive. And any portion that's negative becomes positive. So if it goes through negative 6 down here, it has to go to positive 6 up here. So I'll sketch that in. So this right arm was a reflection of the negative part of the graph of y equals negative 3x minus 6. We're interested in the x-coordinates of the points of intersection. So we have points of intersection when x is negative 3 and when x is negative 1. We only need the x values because the original equation only contained x's. Now, graphing is difficult to do accurately lots of times, so we check our answers in the original equation. So in the case of x equals negative 3, I substitute the negative 3 in. I get 9 minus 6 inside those absolute value signs. Absolute value of 3 is indeed equal to 3. Likewise, when I check the negative 1, I get balance. In this next one, I have a linear absolute value of a linear expression and a linear equation on the other side. So I have y equals 4x minus 1 for my right side. Let's graph that. I could graph that by finding the x and y intercepts, but I think I'll do this one by slope, which is 4 over 1, and y-intercept is negative 1. So y-intercept's negative 1, up 1, 2, 3, 4 over 1, 1, 2, 3, 4 over 1 to get a few points for accuracy. So I have that graph sketched. Now I'll do the graph of y equals absolute value of x plus 5 by the reflection method again. So I'll look at y equals x plus 5. Its x-intercept is 0 equals x plus 5. Put in 0 for the y. We get negative 5 for the x. For the y-intercept, put in 0 for the x. And we have y equals 5. So we've got negative 5 for the x-intercept, 5 for the y-intercept. That gives us our guiding graph. The part that's positive stays positive for the absolute value graph. And the part that's negative reflects across the x-axis. And we've got this arm. We're interested in the x-coordinates of the points of intersection. There's only one point of intersection by the looks of things, and that occurs right here. Point of intersection when x equals 2. So I'll check that x equals 2 by plugging it in both sides of my original equation, like so, and it turns out 2 plus 5 is 7. Absolute value of 7 is 7. 4 times 2 minus 1 is also 7, so we're good. Next, we have the absolute value of a quadratic expression equal to a linear. The linear function has slope 2 and y-intercept 2. So I can graph that one fairly quickly. y-intercept 2, up 2 over 1 for the slope to get some points. Now for the absolute value graph, I really need some good accuracy, so I'm going to do this one by table of values. So I set up my table, and I'll start it with the vertex. That gives me 2.25 for the vertex. Now it was originally negative, so it would have been 0.5 and negative 2.25, but it's going to get reflected up here. Now some other convenient values. Going to the right of 0.5, I'll go with 1, 2, 3. So I have a point at 1, 2, that's a half a unit to the right of my vertex. So I've got a point a half a unit to the left of my vertex. So right away I have a point of intersection with the parabola, or the absolute value graph rather, and the line. When I put in 2, I get 0, and that's going to be an x-intercept. And that is 1.5 spaces to the right of the vertex, so 1.5 to the left. I've got a corresponding point, and it looks like I've got another point of intersection between the two graphs. When x is 3, y is 4, so I have a point right here at 3 and 4, and that's 1, 2.5 units to the right of the vertex. So I have a point 2.5 units to the left of the vertex, right here. So I sketch in that graph based on what I have so far. Looks like this arm will intersect the line somewhere up here, but it's hard to know exactly where. Maybe another point in my table would help. And it looks like when I put in 4 for the x, I get 10 for the y. So I have a point way up here, and now I can complete my graph. Like so. So I have solutions at x equals -1. We have a solution when x is 0. And we have a solution when x is equal to 4. I'll leave the checks to you. When solving an absolute value equation graphically, graph the left side and the right side. Find that's of the equation. Find the points of intersection. If there are points of intersection, the solutions are the x-coordinates. You should check solutions in the original equation.